Assalamu alaikum students. So let's continue from where we left the chapter of the benzene compounds. Previously, we had completed up to the nitration reaction of the benzene and methylbenzene. In today's topic, we shall start from alkylation or acylation of the benzene compounds or methylbenzene. This reaction is also called as Friedel-Crafts reaction. Basically, Friedel-Crafts reactions contains two reactions, the alkylation and acylation. We know that alkyl means any alkyl group, and acyl, as introduced the new functional groups in A2, that was the acyl chloride. That acyl chloride is termed here acylation. So in this topic, we are supposed to find the way of connecting the alkyl group on the benzene ring, that is called as alkylation, and how to connect the acyl part on the benzene ring to make it like a ketone compound. So if we substitute the alkyl group, then we do need the alkyl carrier compound. So Friedel-Crafts reaction results in the introduction of the side chain into the benzene ring. So side chain could be alkyl or it could be the acyl compound. Use a Friedel-Crafts reaction to substitute the hydrogen in the benzene ring for an alkyl group such as methyl or an ethyl. So here are the examples when methyl is bonded or substituted instead of the hydrogen, and when ethyl is substituted instead of the hydrogen atom. We can also substitute an acyl group. So the acyl group is mentioned here, and the acyl group, as you know, is the one in which R is bonded with carbon containing the acyl part or the carbonyl part, and along with that it is there is Cl. This is the acyl group, but we are supposed to connect this carbon with the benzene ring. When this carbon will be bonded on the benzene ring, we will get CO and R. This is R over here, methyl or ethyl or propyl whatsoever. This is the reaction. We can see here that benzene is being reacted with the alkyl carrier compound. The alkyl carrier compound over here is a haloalkane. So we can see that it is the chloroethane reacting with the benzene in the presence of the halogen carrier or catalyst to make the alkyl group bonded on the benzene ring. So this will become ethyl benzene. Or we can also connect the acyl part on the benzene ring, but here we need the acyl chloride. In this case, it is the methyl methanoyl chloride. It is ethanoyl chloride. This compound is ethanoyl chloride. Now this is connected or reacted with the benzene, and we get the phenylethanon. Why is it phenylethanon? We have this phenyl part over here, and then we have the ethanol part over here, two carbon atoms along with the presence of the carbonyl group. The mechanism of Friedel-Crafts reaction involve attack on the benzene ring by an electrophile. So electrophile is the attacking material or the initiator over here, which will attack on the benzene in the start. The electrophile carries a positive charge on a carbon atom, so there is an attack by a carbocation. The electrophile is formed by adding an aluminum chloride catalyst to the halogen alkane to make an alkyl benzene, or to an acyl chloride to make an acyl benzene. Basically, we are reacting the catalyst with the alkyl containing compound or the acyl containing compound. The alkyl containing compound is the halogen alkane, and the acyl containing compound is acyl chloride. Over here, it is the alkyl containing compound, which is chloroethane. It reacts with the catalyst to generate the carbocation, which is the electrophile here. So electrophile is generated here, which will attack on the electrophile, which is the carbocation here, which will attack on the benzene ring along with the formation of AlCl4. So we can see here direction of the carbocation as a catalyst or as an electrophile on the benzene. There is a breaking of the double bond from this point in, and then we have a hydrogen bonded over here. Along with that, we have the alkyl group present over there. And then the second step, the second part of this reaction, which is AlCl4 negative, it will now become a nucleophile to attack on the positively charged compound because we have the positive charge inside of this benzene ring. So what will happen? There will be bond breaking of hydrogen over here in the hydrolytic fission. The hydrogen will be removed. It will react with the AlCl4 negative. And as a result of this, you will have a bond between hydrogen and one of the chlorine from here that will produce HCl. And when the Cl is removed from here in the form of chloride ion, we will get AlCl3 back. So since we call it as a catalyst, it is now regenerated at the end of the reaction. Now we are left with the alkyl group bonded in the benzene ring. Further alkylation of benzene ring can take place as the reaction proceeds, which means we have the mixture of the halogen carrier compound and we have the catalyst inside that can proceed further to connect more of the alkyl groups on the compound. So here is the case. Here we are going to discuss the acylation. In acylation, we again need an acyl carrier compound. So acyl carrier compound is ethanoic right here. Again, it reacts with a catalyst AlCl3 to generate the electrophile carbocation. Now this electrophile carbocation will now attack in the similar way with the benzene ring, just like in the previous case. We have a bond breaking from the benzene part, from the pi electron, from the delocalized electron, and here is a bond breaking process over here. It is shown in the opposite direction of the already attached methyl group. So when it is broken off from here, we have positive charge which is spread over 5 carbon atoms, 1, 2, 3, 4, 5. And this whole seal, the whole of this SI part is connected with the benzene through this carbon atom. So this carbon is making bond with the compound over here. We should remember that in the previous class we said that methyl is a 2, 4, 6 directing group, which means the incoming substituent must be attached on one of these three positions. So starting from here, if it is 1, then the incoming acyl can be attached on position number 2, that could be this one. 4 is over here and 6 is over here. This is 2, this is 4, this is 6. So that's why we can see that the more uh, the more feasible site or more feasible position for the incoming acyl is on position number 4, and we can see here. So carbon is bonded here because it is a electrophile. And then the same way, the next steps include the same thing. There is a hydrolytic bond fission of hydrogen with the benzene ring, and there is reformation of the pi electron inside the benzene ring to complete the benzene ring. And the loss of this hydrogen reacts with this AlCl4 negative to make HCl and AlCl3. So it is regenerated. The same topic is mentioned in the other source book. It is again the overall reaction, benzene reacting with the alkyl carrier compound, which is over here chloromethane. It reacts in the presence of Cl3, AlCl3, and we find two products here, the methyl benzene and the HCl. And if we have already a methyl compound, a methyl benzene compound, which is reacting with the same CH3Cl, we find that the second methyl is bonded in position number 2. It could also be on position number 4. It could also be on position number 6, since we know 2 and 6 are same. And over here, it is bonded on position number 3. Over here it is bonded on position number 4. Basically, this one has a least percentage in yield, whereas this one and this one has a higher yield. There is a higher percentage of these two compounds, and this one has a least percentage. So what about here? This is this mechanism explained. We have chloromethane reacting with the AlCl3 to make this intermediate. Now this intermediate is converted into carbocation along with AlCl4 negative, and then the attack on the benzene is through the carbocation. So this is benzene, this is carbocation. We get the same intermediate, and then reformation of the benzene ring or pi electrons. And acylation is also explained more. We have the reaction between benzene and ethanoic chloride. We get phenyl propanone ethanone. Sorry, it is phenyl ethanone, and then we have the mechanism in the same way. This thing is mentioned with the proper name called acylium ion. We have already seen this species in the previous case, acylium ion, which is obtained from the acyl chloride in the cation in the carbocation form. Over here, this is a methyl compound, methyl benzene reacting with the ethanoic chloride to have the substituents at position number 2, at position number 3, and position number 4. 2, 3, 4. But we know that this product and this product are already in higher proportion as compared to the central compound, since it is present on position number 3. Now the next topic is the oxidation of the side chains. We have the benzene compounds in which there is some alkyl group already attached. So it is a alkyl benzene, or we call them alkyl arene. You can use the word alkyl benzene or alkyl arene. And in this case, the alkyl part is a methyl. Now this methyl can be reacted with the oxidizing agent. So the oxidizing agent here is potassium manganate 7. So what happens during this reaction, that the alkyl group is basically oxidized into the carboxylic acid part. In the presence of oxidizing agent, it will be oxidized to carboxylic acid in the presence of the alkaline KMNO4. So we do need to use alkaline. It could be NaOH or it could be KOH. And also to be refluxed. This is the reflux topic which we discussed in the AS level, in which there is a round bottom flask connected with a condenser, and we have the organic compounds in a liquid form inside the round bottom flask. They are heated by some electric method. The compound evaporate and they condense back into the liquid form, and this keeps on going on for the reaction to complete, because organic compounds can easily evaporate it, so we have to make them complete by doing this way. So oxidation of any of the alkyl arene will always produce one single product. Two products will be there. The formation of the benzoic acid along with the formation of the carbon dioxide and water. Basically, here we are doing the oxidation of the alkyl chain bonded with a benzene ring. So here, again, we are using alkaline KMNO4 as a medium, and it reacts with the alkyl chain. Then we have the salt of the compound produced during the intermediate stage, and then when it rejects the acid, it converts into benzoic acid. So whatever length of the alkyl chain is there on the benzene ring, it will always be converted into the carboxylic part. However, the rest of the carbon atoms of this alkyl chain, it could be 1, 2, 3, they always produce carbon dioxide in the equal amount, because we do have to represent the carbon dioxide as a byproduct So they should have the same number of carbon atoms which were oxidized here. So if it is methyl, then we get benzoic acid, and if it is, even if it is propyl part, we still get the same product. Carbon dioxide, sorry, benzoic acid, along with the formation of carbon dioxide plus water. And in this reaction, there is a change in the color. The color change is from 7 of the manganese to Mn plus 4. So Mn changes from plus 7 to plus 4, and the color is brown. In case of Mn plus 4, it is brown, and if you remember, Mn plus 2 was pink color because it is a transition element. So transition element can exhibit different colors in their different oxidation states. So that's the reason that we say it is forming a brown color compound, and the other carbon atoms are removed in the form of carbon dioxide molecules along with water. So the same reaction is mentioned here. Over here we have now two alkyl chains on the same benzene ring. We have ethyl. Over here we have ethyl and methyl. So you can see that the product contains firstly the salt of the carboxylic acid because of the presence of K. But then when it reacts with the acid, which was previously H2SO4 mentioned here, then that K will be replaced by the hydrogen atom to make the carboxylic acids. So both the alkyl groups are converted into the both the carboxylic acids here. So we have done up to this point. We'll continue our next topic in our next class. Till then, take care and Allah Hafiz everyone.